Hi, everybody. So now let's talk a little bit about crystallography. Um, crystallography is the study of solid objects where the atoms or molecules that make up the object are arranged in a lattice. That is to say, they're sort of in a grid in 3 dimensions. And the structure of that grid adds strength and rigidity to the crystal. And also the symmetries of that grid lead to the shape of the crystal. And trying to understand the possible shapes of crystals was an important problem in chemistry and in geology for a long time. And the mathematical approach to this started maybe late 19th century, early 20th century, where the question became, can one actually classify all of the possible rigid arrangements in 3 space? And that was finally concluded with an answer of 230. There are 230 possible ways to construct a crystal in 3-dimensional space. And understanding this is related to the ideas of the Euclidean group of symmetries that we've talked about in the previous videos. So I want to introduce some of the ideas behind that and then talk not about the 230 crystals in 3 dimensions, which is pretty complicated, but the simpler case of what you might call crystallography in the plane. These are sometimes called wallpaper patterns, and they are symmetries of repeating patterns in the plane where you have something which laid out in a grid, and then you try to understand all the symmetries of this stuff that lives in a grid. So we'll introduce some basic ideas and then talk a little bit about that either in this video or in the next one. Great. So let's start with the idea of a lattice. A lattice is a subgroup of the real vector space in n dimensions, which you get by taking a basis of that vector space and then taking linear combinations of it with integer coefficients. So it's maybe easier to explain this with a couple of examples. Let's start with maybe the simplest example. Take R2 and take the standard basis, I and j. And now the lattice that we're interested in, L, is the collection of combinations of I and j, but not with all real coefficients, which would give you the whole plane, but just coefficients that are integers. And if you think about what you get here, you get I and j and I plus j and 2i, and maybe also here this is I minus j, and so on. And when you just take integer combinations, the points that you get lie on a grid with square sort of cells. And from that, you can kind of see why this might be called a lattice. A lattice is what you get if you have crossing lines, like if you make a fence with crossing strips of wood. That's called a lattice, and this looks like a lattice. Although strictly speaking, the lines here are not part of the lattice. The lattice itself are just the intersections of the lines, just these points. If you do this in 3 dimensions, you get a picture which looks like this. Here, the basis for R3 have these, let's say these 3 vectors, maybe this one, and this one. And then you take all integer combinations of those and you end up with the points that are marked in black here. So this one here is maybe the sum of those 2 basis vectors and then the sum of those 2 basis vectors. And here, to get here, you would take the sum of 3 of these basis vectors and so on. And so you end up with a grid where each cell is kind of spanned by the original basis vectors. So the shape depends a lot on how those vectors lie. But regardless of the shape of the lattice, as a group, lattices are very simple. A lattice is just a subgroup of the real vector space in n dimensions, which is isomorphic to the Cartesian product of the integers with itself n times. So remember Zn here. This is the collection of vectors a1 up to an, where the ai are all integers, and you just add component-wise. And the map f from Zn to L contained in Rn, here L is the collection of integer linear combinations of a basis is you just take a vector and you convert it to a sum of the basis vectors using the elements of your vector of your element of Zn as the coefficients. And to see that this is a homomorphism, you can check that, that f of a1 up to an plus f of b1 up to bn is sum ai xi I equals 1 to n plus sum bi xi I equals 1 to n. And you can regroup that to be the sum where you take the coefficients of the basis vectors and collect them. But that's just f of a1 plus b1 an plus bn, which is the sum in Zn. So it's a group homomorphism. How do you know that it's bijective? Well, to check that it's injective, it's enough to check that if f of a1 up to an equals 0, then actually all the coefficients are 0. In other words, you check that the kernel is the identity. And so suppose that's true, well, that means that the sum of ai xi equals 0, but the xi are a basis. So they're linearly independent. So the only way you can have a sum equaling 0 is if all the ai are 0. And that means that the original element of Zn was 0. And that shows that it's injective. And to show that it's surjective, if you have an L in L, and you write it as sum of ai xi, which you can by definition, then f of a1 up to an is L, because this is sum ai xi by definition. So a lattice, the sort of, if you were going to draw it, it depends on the basis vectors. But as a group, it's just a collection. It's the group of vectors of integers of length n. And all lattices are the same group, even if geometrically they may look different. Now, we can ask for linear transformations which carry the lattice into itself. And this is called the automorphism group of the lattice. And one way to think about that is, to make a lattice, we picked a basis for the vector space. But sometimes it can happen that we pick a different vector space, different basis, we get the same lattice. For example, in our very original example, I described L as the collection of integer combinations ai plus bj. But that's the same as the collection of linear combinations ai plus b minus j. Or the same as the collection of linear combinations ai plus bi plus j. All of these give the same lattice, because in this case, it's just, if I want ai plus bj, I just change the sign of b. And here, I can get, for instance, if I want just j, if I take b to be 1 and a to be minus 1, I get I plus j minus I. So j, I can get j in here. And if I look at the collection of points that I get in the end, they're all the same. And the unimodular group in n dimensions, GLN, and it's written GLNZ, but as we'll see, this is not the collection of integer matrices with non-zero determinant. It's the collection of integer matrices with determinant plus or minus 1. This is the collection of G which carry a lattice to itself. And let's check that out, but to make our lives a little bit easier, let's look at the n equals 2 case. So our lattice L is spanned by two vectors, E1 and E2. And so L is the collection of AE1 plus BE2. Now, suppose I have a vector of G, which is a matrix. And suppose I look at GL, and the question is GL equal to L? Well, to check that, we first ask is GL contained in L? And, well, actually, let's do it the other way. Let's ask if L is contained in GL. That's maybe a little easier. So what is GL? GL is the collection of combinations of a different basis, namely the combinations of G of E1 and G of E2. And you can see that because if you apply G to AE1 plus BE2 and use linearity, that's AG of E1 plus BG of E2. So GL is the lattice that you would get if instead of starting with E1 and E2, you started with G of E1 and G of E2. And L is going to belong to GL if and only if E1 and E2 are in GL. Because if E1 and E2 are in GL, then all integer combinations of them will be, because GL is a subgroup. So 2E1, 3E1, 3E1 plus 5E2, they will all be in GL. And that would mean that E1 has to equal, let's say, AG of E1 plus BG of E2. And E2 has got to equal CG of E1 plus DG of E2 for some A, B, C, D, and Z. And now, if that's true, suppose under what conditions are GL contained in L? Well, that would mean that we have to be able to write G of E1 and G of E2 in terms of E1 and E2. And if we view these as two equations and two unknowns, what we find is that G of E1 is equal to DE1 minus BE2, but that we have to divide by AD minus BC. And G of E2 is 1 over AD minus BC minus CE1 plus AE2. In other words, if we look at the matrix G, let's look at the matrix U, which is A, B, C, D, then its inverse is U inverse DA minus B minus C 1 over delta, where delta is AD minus BC. This is just something we've used before, and it's a little trick with 2x2 matrices. If you multiply these two matrices together, you will get the identity. And what we've shown here is that GL is equal to L if and only if U has integer coefficients. That's the A, B, C, D from these equations. But also U inverse has Z coefficients. Because if you expand this out and look at the coefficients of E1 and E2, if G of E1 and G of E2 are in the lattice L, they have to be integer combinations of E1 and E2. And that now, if we use the fact that U and U inverse are inverse matrices, we know that the determinant of U inverse has to equal 1, because U inverse is the identity. And that means that the determinant of U times the determinant of U inverse has to equal 1. But if GL equals L, both of these matrices have integer coefficients, so these are both integers. I don't know what they are, but they're integers. And if you have two integers whose product is 1, there's only two possibilities. They either both have determinant 1 or they both have determinant minus 1. So we conclude from this that AD minus BC has to equal plus or minus 1. And that G, the matrix that we're interested in, G, which is in GL2 of Z, has to be a matrix determinant of G plus or minus 1. And that gives us that the unimodular group consists of 2 by 2 matrices. If you want to do this for n by n matrices, this is essentially Cramer's rule. And Cramer's rule tells you that an n by n integer matrix is invertible, with its inverse also having integer entries, if and only if the matrix has determinant plus or minus 1. The thing to be careful of is that despite this notation, it's tempting to read this as n by n integer matrices with non-zero determinant, but it's integer n by n matrices whose determinant is plus or minus 1. That's the unimodular group. Okay, in the next video, we'll take up this question about crystallography.